with the topic that says system level diagnosis. So like I said, this is going to be my last contact with you, and then Mr. Chibo will take over. I met him yesterday. So by the end of this lecture, we're going to look at students are supposed to be able to demonstrate an understanding of the process of diagnosing system faults at the level of the system and implement techniques to isolate and diagnose faults. This is not going to be a difficult one. So yesterday, what did we do yesterday? We started talking about modeling availability and the reliability of a system. Now, assuming a system has issues, how do we start diagnosing the system to see if there's any fault in the system? In passing, by way of illustration, I made mention of that when I represented a kind of a high-level overview of a computing system or a computer, where we have the power supply, we have the two fans, we have the processor, and then you have the hard drive, whatever. And then you know that that's actually not, that's just the block diagram, a high-level diagram of what we can see in the system. There are other components that you will get from one place to the other. You will meet going from one place to the next line. There are other components. So it's not as if it's as small as that, but having a picture of the architecture of that system in mind, you know how you proceed from the power supply even to the output of the system, which in some cases the thing is going to end at the memory, some going to end at the visual display unit, and so on and so forth. Okay, so system level diagnosis actually refers to the process of identification and isolation of faults in a complex system. The process of identifying that there is a fault and then bringing that fault aside. Okay, that's isolation of that fault. So we have a complex system and there's a kind of performance in one place or the other. And then we needed to check where this thing is. What are the things, where this thing is coming from, and what is the cause? Notice that I'm mentioning two things. Where the thing is coming from, that's where the failure is occurring, and how it affects the overall system performance. In other words, what is it that brought about it and what is the output of this? Now we're able to understand what the outputs that a certain misbehavior can bring. It will give us understanding into being able to separate and to say, okay, this is what is happening to this system at this point in time. So at this level, it is very, very necessary to be able to pinpoint this because it will help us to maintain system reliability and performance. In other words, prolong how far the system can serve us before it gets down. So if we have a vivid understanding of the system, we know that if a failure is to occur, then there are certain places that we may need to get at, or rather, to get at. Now, it's sounding rather a kind of hardware in mind, but I also want you to begin to see when I talk about components, because there's something that is known as component-based software engineering, which, or rather, let me use the word that you may be so familiar with, modules and packages. Now, when you are developing your software-based systems, you know that at some certain point in time, you are importing modules or importing packages. Now, if you have the understanding of how the behavior of a package or a model affects the overall system. When a system begins to misbehave, when the system that you've developed begins to misbehave, you will be able to directly know that, okay, maybe a certain package or a certain model is misbehaving or is out of date, and so on and so forth. So the understanding of this helps us to minimize downtime by enabling quick detection and correction of faults, because we have an understanding of how the system is working. So it helps us to predict maintenance. Okay, it helps us to predict maintenance. And if we're able to predict when we need to perform maintenance, then there is a reduction in the likelihood of the system breaking down. All right. So the overview of system faults, as we've discussed before, categorized faults into three broad categories. We have the permanent faults, which occur when a component is permanently damaged and stops functioning. Like I made mention of your CPU, sorry, your motherboard in a computing system getting destroyed, maybe by thunder. You will not pray to raise it back. You're only going to pray. You're only going to pray that God gives you money to replace it. Okay. So we have transient faults, and these ones are temporary malfunctions that resolve without intervention of the developer. But the truth is that it might still disrupt the system operation. Okay. And then we have intermittent faults, and these are faults that occur unpredictably, and they are hard to diagnose since they appear and disappear over time. And I told us that these faults may come as a result of maybe environmental factors. Okay, maybe maybe the operation of waves around the environment where the system is being operated. We have types of system faults that we can counter in the process of our work. Number one is hardware faults. And these ones are physical failures that we can notice: the power surge, overheating, component wear, and so on and so forth. So there is a hardware fault. For instance, in your car, although the brake system may have been computed to show on the dashboard using some embedded system software, okay? But the truth is that if the brake pad wears out, although the software aspect may be working, but the system is bad. So we see an interface between software and hardware, okay? So at that point in time, that particular kind of failure is actually a hardware fault. And then we talk about software faults, and these ones are a kind of misbehavior in the program that you have written to control some certain things. So these ones are hardware faults. So the software faults. The hardware may be intact, but because of the bug in the software, the system may not be functioning well because the interaction that it needs, the control which is performed at the software base, is not actually working properly. And that may lead to communication faults like network issues, signal degradation. Please, can you mute yourself if you are the person whose network is having issues? Can you mute yourself? Garba Aminu. Okay, next we have communication faults, which may come as a result of network issues, signal degradation, and protocol failures. And there could also be a link between the software faults and the communication faults, all right? Because the software is actually the system, I mean in an embedded environment, embedded system environment. Okay, because the software is actually the system that controls the communication between one component or the other in the hardware environment. All right, so if the software has a fault, it may not be able to send a signal to another area to start operation. Let's take, for instance, you programmed an irrigation farm, and the farm is supposed to work because at some certain detection, at some certain maybe temperature level or humidity level, the irrigation is triggered to function. Now, it's triggered to start, that's to start functioning. Now, at that point, if there is some bug with the software, it may not be able to trigger an operation that necessitates an actuation of the valves so that the field will be watered. Okay, so you now see that there's an internal communication fault, which may be orchestrated because the hardware also has an issue. Okay, so all of these things can relate with each other in one way or the other. So we have to have understanding of these. So if you are programming a system, there is also need to check to see the hardware that I'm about to control, is it intact? The communication lines, are they working properly? Okay, so if there is proper communication between one component and another, and then you are needing, and those components are also good on their own, because you may be, there may be a good line, a good communication link between one sensor and an actuator in a system. But because the sensor is bad, it may not be able to receive signal. So that's actually a hardware fault. Means that before the system will work, you need to change the sensor itself. All right. So all of these things come together to form a system fault. So in a complete system, there is hardware, there is software, and there is a communication system linking the components of the hardware. All right. Now, what is the process of diagnosing system level faults? We say that the number one is monitoring and data collection. There is need to monitor the system and then collect data concerning the operation of the system. And then after monitoring, we can now use that data to isolate faults in other words, to say that this fault is coming from this sensor. This fault is coming from that sensor. This fault is coming from this. And then the next thing, if you're able to say that it's coming from this, the next thing is identification. Okay. Now, in identification, we are not just talking about, we are now in the area where that fault occurred. We are now in the area where that fault occurred. Now, we want to know what actually happened for that fault to occur. Okay. And if we are able to identify the cause of the fault, the next process will now be to repair the system. In other words, to deal with that issue that necessitated the fault. So we said that the process involves, first of all, monitoring and data collection, fault isolation, and then fault identification. Let's look at these in detail. So when we talk about monitoring and data collection, what are we talking about? We say that this is the first step. Okay, it includes creating a system of logging errors. Okay, of logging errors. So if there's an error, the error will not just show up, it has to be logged, because it's going to give us an understanding of what has happened over time. Now we can also track events. We need to capture events in the system so as to know which event triggered an abnormal behavior. Okay. So, and then we have to also have a setup that helps us to monitor CPU usage, okay, memory usage, disk IO, network throughputs, and so on and so forth. You know, I used to tell you that the testing aspect of your system is not just that it works. Okay. Now, when you finish developing, let's say, a software system, and you let the software, you put it into operation, you start monitoring the CPU usage, how the system is using the CPU. This could be a metric that you can use to trace when there is a fault in the system. Let's just say that the system started using 10% of the processing power of your machine, and then after a while, it starts using 80%. You know that something is wrong somewhere, okay? The same thing with the memory, okay? And the output of the system. There is need for you to take a measurement of these things and monitor the operation of this, okay? Now, let me give another illustration. Let's assume that you've developed an embedded system that monitors the flow of fluid in a pipe. Okay, that fluid can be water, it can be oil, it can be anything. And then you want to be sure that the entire operation is still functional. Now you may have to mount sensors on the pipes, on the pipe or the length of pipe, depending, and then continue to record the vibration of the pipe when in use. Now, if at any point in time you started recording a higher vibration, it may be a signal, it may be sending you a signal that there is an abnormal behavior or that there is a kind of an attack on your pipeline and so on and so forth. Because you are able to get this because you were monitoring the sensor behavior over time. So at any point in time, you notice something that looks like an outlier. Let's just say that the vibration range is from 0.5 to 1.5, the normal vibration range. And all of a sudden, you start seeing 5, okay, in your vibration range. You will notice that something must have added external pressure on the pipe. And so if that system is actually connected with maybe location sensor systems, the system may also show you the location or kind of give you the address location or the model or the kind of node that is actually giving that abnormal behavior. And then you can trace it immediately. So this is how monitoring and data collection works, okay? So because the data you've collected over time, you can put it in a machine learning model to predict what is happening to the system per time, all right? So the next one is fault isolation. So once the data has been gathered, okay, while you have gathered the system, the next step is to isolate the system. Okay, and the steps involve hypothesis generation, and this is based on the data that you have collected. Okay, and this is based on that data that you have collected. And perhaps when a system fails, you may look at the time the system failed and the nature of the data, and you can be able to say that this possibly is the cause of the system failure. Okay, this possibly is the cause of the failure at that point in time. And then you don't, at that point in time, it's just still a hypothesis. You have not really confirmed it. Now, how are you going to confirm it? You're going to confirm it by now testing the subsystem, running diagnostics on the suspected subsystems or components in order to verify if they are actually the source of the fault. Now, if you go to that place and you see your sensors, you started looking at the sensors, checking if the sensors were misbehaving, because a sensor misbehavior can lead to an abnormal behavior and not necessarily saying that there was an attack also. So you can check the sensors and find out that the sensors are intact. Then it means that perhaps there's an external force that was dealing with the system at the point of the information you gathered. Okay, and also you may find out that actually the sensor is giving a wrong value at that point in time. It's not necessarily because There was an external attack. So by that, you have actually isolated the fault. And that leads us to this. If you have isolated there's a fault in this place, in this particular component of the system, the next thing is what then was the cause of the fault. So after isolating the fault, the exact nature of the failure has to be determined. And this will involve, number one, root cause analysis. Now, what is root cause analysis? On finding the underlying cause of the fault rather than just the symptoms. Because when you were testing, you may notice that the system was actually giving, the sensor in operation was actually giving an abnormal value. But the question is, what is the cause of the abnormal value that the sensor was giving? Because we needed to know if that abnormal value was coming from the input into the sensor or not. Okay. And we may need to find out at the point that this thing happened, or rather when it started giving the abnormal behavior, we now go back to the error log to find out, was there a system of recording the voltage that was going into the sensor at that point in time? So if there was a system of recording the voltage at some certain point in time, you may be able to find out, okay, this thing was actually destroyed because of a surge, a power surge, a voltage surge into the system. So you now have an understanding of what actually caused the destruction of that particular component. Okay, now it may not be, but it may still be as a result of a bug that was introduced into your code by some certain circumstances. Okay, now when you have found out that possibly this was as a result of this and this input into the system, you now try to model the same thing in a controlled environment. That's what we now do when we're talking about testing scenarios. Okay, you reproduce that fault in a controlled environment to better understand how it behaves. For instance, you will get a sensor and try to pass a certain amount of voltage into it to know what will be the reaction of that sensor towards the voltage input. So if you're able to get, okay, indeed, the failure of this particular sensor was as a result of a surge, then you have established that you have gotten an understanding of that. So when you've gotten that particular understanding that this is actually the cause of the failure of that component, the next thing now is to repair. Okay. Now, the systematic repair and resolution is what we're looking at here. Once the fault is identified, the final step is to apply a fix. And this could be hardware repairs or replacement when it has to do with physical components. Or if you found out that actually it was a software misbehavior, you need to now talk about developing updates in order to deal with the system bots, okay, that caused it. And in some cases, especially for transient issues, you may just need to reboot your system and everything resolves. Okay, so that is what we have in system repair and resolution. And that's the complete stuff. Okay, the first one is monitoring the system and gathering information about the system operation. And the second one has to do with fault isolation. And then when you isolate the fault, the third one has to do with fault identification. When you now say, okay, this is the cause of this fault. And then the fourth one is repairing the system. And so you have brought the system back to normal. What then are the techniques that we can use in this fault diagnosis? Number one is that when you are developing the system, you kind of build it to have a built-in self-test. In other words, as for instance, when your system is booting up, there are some certain operations that are testing the performance of your system. Okay, whether your hardware is intact, whether your memory is intact, and all of those things. So the system now at booting point, it start testing some stuff. Okay, then you have watchdog timers. Okay, and these are kind of things that you put in place to continue operation or to stop operation, for instance, when a certain system fault is triggered. Okay, we say that built-in self-timer is a mechanism where the system performs self-testing at startup or during operation to detect whether there are internal faults. And it's useful for identifying hardware faults without needing external diagnostics. Now, you are the person that needs to set up this. So at the beginning of your system operation, it tests to see. You can write a program to see if the components are intact. All right. Now you can write a testing script to be able to perform all of these things before the system boots up. Now, what dog timers are timers that monitor software execution. So if a system or task fails to reset the timer in a specific time frame, the system assumes that a fault has occurred and then triggers a corrective action, which may look like a system reboot in some cases. Okay, so that is it. And then next is that we talk about redundancy and fault tolerance. Okay, so when we talk about redundancy, we are talking about having to put several or multiple modules that perform the same operations simultaneously. So if one module fails, the other modules will continue operation. But this is not going to just be like this without the failed module identifying that it has failed. So you also may need to build a component that kind of a dashboard that shows these are the systems in operation. Although the system is still working, but the dashboard is already telling you that a particular module is no longer working. And then another way is to build checkpointing. Okay. In checkpointing and rollback, the system regularly saves its states. Okay, its safe states, not just its states. So in the event of a failure, the system can now go back to the previous safe state, eventually undoing the cause of the fault. Now, this is majorly operational in software systems. Okay, it's operational because if a hardware is already bad, you may not be able to roll back to whatever, because it has to do with something physical. So it has gone bad is that it has gone bad. The only thing at that point in time is to actually replace that particular part. Okay. Now, there's also the use of diagnostic tools. The diagnostic tools will help you to kind of look at what the system is doing per time. For instance, performance monitoring tools like Task Manager in your system, in your Windows, when you open it, you will see what the system is doing at any point in time, the performance of each of the software that you have installed in the system. You also have network analyzers, tools such as Wireshark, that help us to diagnose communication faults in a networked environment. Okay, you have hardware tools, diagnostic tools for testing memory and other hardware components. So you also need to have this in your toolbox. And that is the end for this particular class. So we can have a review example like we are seeing here. We said that a server in a data center is reported to be experiencing intermittent slowdowns and periodic reboots. As a systems engineer, discuss the professional approach or approaches you would use to diagnose and fix the fault for optimum data performance. Now, this question kind of captures everything that we have done here. as a professional engineer, as a systems engineer, what are the professional approaches that you are going to use and why? When you are explaining this kind of question, when you mention the first approach, you tell us what you are going to do there, the second, and why you are doing it. The second approach, you say what you are going to do in that approach and why you are doing that. In third approach, you say what you are going to do and why you are doing that, and so on and so forth. Okay, so that is it for this particular class. I don't know if anybody has any questions before we call this one a day, before we stop this class. Please, if you have questions, you can ask now. Meanwhile, I've stopped the recording.